complete.
Because I know the lithium ion is like something.
By drawing the conjugate acid based on area. I think by now you're familiar with area. We talked about it before, right?
Yeah.
Indicate which one is favored. Okay, so I'm given this. There's a negative charge there. This thing is ionic. And then I have H2O. Okay. And I need to decide where the equilibrium will go. So the first thing is to determine between these molecules, where is my acidic hydrogen? Is it going to be the CH or the OH?
Okay.
Okay, number one, you need to find acidic hydrogen. So where is it? The acidic hydrogen is the one that is, if you're following aerial,
Electronegative atom.
yeah, the one on oxygen, this one. Now, once you do that, the arrow starts from the lone pair to the hydrogen, and then from the bond to the oxygen. That first arrow is showing we are stealing the hydrogen. Can you still see my screen?
Yeah.
Okay. And so that means that we've added our hydrogen there, and our oxygen will now have 3 lone pairs and a negative charge.
Okay.
Because initially we have 2 lone pairs. The one that accepted the hydrogen is going to be the base, and the one that gave the hydrogen is the acid.
Okay.
And then next thing, we want to use the rule. The rule is equilibrium always lies on the side of weak acid, weak base.
Okay.
You're still going to use area to decide, because I think you're not going to be given the pKa numbers.
No. Okay.
Which one is the side with the weak acid?
Is it the H2O?
No.
Is that the weak? No. Okay.
If this is your acidic hydrogen here, this is your acidic hydrogen there. So between CH and OH, which one is more acidic?
The CH?
No. Use area. Atom. Under atom, we use electronegativity. The higher the electronegativity, the weaker the base.
Okay.
And you're looking at carbon versus oxygen. In your periodic table, the second period, those are the elements, and En increases that way.
Okay.
Okay, so.
Okay. So it favors the side that's weaker. So it favors the right side?
It's gonna favor the right side, because the thing is, this one is less electronegative, making this one less acidic.
Okay.
This one is more electronegative. No, wait. Yeah, less acidic, making this one more acidic. But we are talking about base. We are not talking about, I should be looking at the original molecule as I say this. Let's see. Oh, the question is simple. If you look at OH and CH, which one has an acidic hydrogen? Which one has a more acidic hydrogen?
The one with the oxygen.
Thank you. And
Okay.
it's because oxygen is more electronegative. Equilibrium lies on the side of the weak acid. This should be the weak acid, just like that.
Okay.
We don't even need to think much. Equilibrium should be going to the right.
Okay.
Now let's compare the base. Electrons on a carbon versus electrons on an oxygen. Which electrons are not available?
Not available.
Not very much available. Remember, increase in electronegativity equals to increase in basicity. So you are comparing the bases now.
So the carbon ones are less available because.
Oh, those ones are more available because this is less electron attracting.
Okay.
Making this a strong base.
Okay.
I don't know why you are saying the trend and then you say the opposite. Look, what is electronegativity? Ability of an element to hold on electrons.
Okay.
If you're holding on electrons, you don't want to give them away.
Mm-hmm.
So if you're less electronegative, that means you are so generous you want to give away your electrons, then you're more basic.
Okay.
So this is a stronger base. This is a weaker base. So I'm showing you that you can decide using the acids, because this is the conjugate acid, this is the conjugate base. You can decide using the acids, or you can decide using the bases. The equilibrium always lies on the side of weak acid, weak base.
So the more acidic, the less electronegative. So that's the opposite of the basicity.
No. It's the opposite. When you're talking about electronegativity, if a hydrogen is attached on a more electronegative element, then that means the electrons bonding to that hydrogen are not available. That hydrogen can easily be given out. It's acidic.
Okay.
Which is why I'm telling you, increase in electronegativity is decrease in basicity, meaning increase in acidity.
Okay.
Of the parent acid.
Okay.
So I've shown you two ways on how to decide that.
Okay.
Equilibrium lies on the side of the weaker base. Carbon does not hold on the lone pair very well compared to oxygen. So carbon is more basic than C minus is more basic than O minus.
Okay.
Mm-hmm.
Okay. Maybe let's do another one to see if I'll figure.
No. Just
Oh.
kidding. Just kidding. Just kidding. Let's do it. Am I able to say?
And then if there's the lithium's an ion, right? Is that what that's called? An anion?
The what?
Or anion? That's lithium, right?
A lithium cation, yeah, that's an ion, but it's a cation.
Okay. So when there's a cation present, always just split it and like detach it from the molecule.
Yes. And we are going to do that for the second one. Then I'll give you my own.
Okay. Yeah.
So we have to decide which direction is favored. So like you said, exactly. Na plus is not doing anything here. It's just for motivation for the NH2 minus. But this side we don't have a metal, so don't ionize. Now you decide which one is more acidic. NH versus SH. Which one is more acidic?
I want to say the SH because of size.
We don't consider size. Size is only when the elements are in the same group. These are in generally left-right, different.
Let me look at the periodic table.
Different groups. The periodic table will have CNO. Sulfur is somewhere down here.
Okay.
So you generally sulfur is more electronegative.
Okay. Okay, so you move over. Okay. Okay. So
Yeah.
since it's it was nitrogen, oxygen, and then sulfur below. Since it's a one row over, I would take into account electronegativity over size.
Yeah, size is only when they're exactly on the same column.
Okay.
Like OS or FClBr, I.
Okay.
Or even OSSE, I think. I don't know if we have TE there. I don't remember very well. There's phosphorus here. Or NP.
Okay.
Those ones is when you consider size, generally.
Okay. So if they're not in the same row or column, what do you like? How do you determine which one to use?
Electronegativity. I'm going generally to the right.
Okay.
Usually you prioritize going left-right when they are not in the same column. Although there's a table that I usually give students, table of electronegativity. It has the electronegativity values called Pauling scale periodic table.
Okay.
Okay, so this is more acidic. So which means this will play the role of a base. That said, you see the negative charge, it has to be the base.
Is that always true?
Yeah. The one with the negative charge and another one is neutral. The one with the negative charge will be the base.
Okay.
Always
is
true.
that only if the other one is neutral?
Correct. If both of them are negative, then both of them are bases. And most likely they will not react because like charges repel.
Got it. Okay.
The answer will be no reaction because like charges repel unless there's a very acidic hydrogen somewhere.
Okay.
Which is rare. So we do the normal arrow pushing, still the hydrogen, and we break the bond. Our NH is happily now NH3. It had 2 lone pairs, now it's 1. No formal charge anymore. The sulfur right now has 2 lone pairs of electrons.
Okay.
It's going to have 3 of them now. And you can tell this is a conjugate base again because of the negative charge. While this one, ammonia, is a base, in this case it's gonna be the conjugate acid because you have another one that is negative.
Okay.
So your role is to compare these two and tell me which one is the weaker acid. Use the same idea.
Okay. The weaker acid. It's the NH3. That's the weaker
Correct.
acid.
So the direction is gonna go this way.
Okay. And then, silly question, but the tail of the arrow can never go off a charge. It can only go off lone pairs in a bond, like a double bond or a bond. Or not.
Yeah. Authors will start the arrow from a negative charge. That's so dumb. The right way, you have to start from the lone pair. The negative charge there is just telling us we have an extra electron. So arrow should not start from the positive or from the negative, sorry. It starts from the lone pair or a bond.
Got
Now you using the acids, you see the reason. Now let's try use the base and see if it agrees. That's the base conjugate base pair. And still you're going to see that this is the weaker. Why is that the weak conjugate base?
Because it's more electronegative.
Yes. And so I told you, you can use either the acid to decide or the base to decide. The equilibrium lies on the side of the weaker base, weaker acid.
Okay. Okay.
Yeah. And now you tell me the answer to this one then.
You gave me an alkyne?
Yes. That's how much I love you.
Thanks.
You tell me which direction we are going. We talked about terminal alkynes, and I believe you have an idea. I believe you have an idea of acidity of terminal alkynes, correct?
Yeah, I think.
Okay.
I just know that like
Uh-huh.
in Oreo, sp orbitals are the most acidic.
You're right.
Yeah. Okay.
And you can use your cheat sheet to you say, oh, I have a negative charge. So this must be a base. And then here you have a catch. You have to decide which of those hydrogens is more acidic. He has to be this one because it's sitting on sp. These ones are sitting on sp3.
Okay.
Remember the orbital factor in aerial? That's what we are using here. Orbital, it goes with hybridization. So this plays the role of an acid, and then you'll describe where the arrow begins, where it ends.
The arrow starts on the lone pairs and goes to the more acidic hydrogen.
Okay. So we start from one of these, lands on the H, sp, ch, and then a follow-up arrow goes on the other side. That way, you're going to keep that carbon, but now he has a lone pair. If you do the formal charge calculations, it will be valency of carbon is 4, minus 2 dots, minus 3 lines, it's negative.
Okay.
On the other side, you're going to have water. This will be a conjugate base. This will be a conjugate acid. Now decide the direction. We need to know the direction. I'll let you digest that and tell me.
I don't know why I'm so confused.
You're confusing yourself. That's why.
Wait.
Mm-hmm.
Is it the OH that's more acidic? No?
Look. Is OH an acid right
That's
now?
more basic. That's more basic.
So you are either thinking about who is the weaker base or who is the stronger acid. So you have to focus. If you are looking at OH, then you're looking at the conjugate base and compare who's carrying the negative charge in the conjugate base, who's carrying the negative charge in the base, and who is more electronegative. That's going to be the least basic.
Okay, but I don't know why I'm so confused because it's two oxygens, so they have the same electronegativity, right?
Where is the other oxygen?
In the base, so I'm not allowed to look at that.
You're saying there are two oxygens. Where's the other oxygen?
No, I'm stupid.
You're not. You're confusing yourself. I told you. Let's
I
do
think
this.
the
Let's compare
that's stronger.
these two.
Am I right?
Huh?
Am I right? Is it the H2O that's stronger
Yeah, H2O is stronger. Is a strong
than
acid
the
because
left?
huh?
It's gonna go to the left.
Correct.
Okay. I was looking at the OH and the H2O and comparing those because I
No.
was looking for electronegative atoms.
No, you always compare acid. That's why we arranged the order. So you know you are always comparing the pair. Acid conjugate acid, base conjugate base. Always. And just by that, you can tell this is not a good base.
Okay.
This is not a good base to do what? To deprotonate
Okay.
the alkyne.
Okay. I was being silly.
You just trying to confuse yourself. You got this.
Trying.
You got this, trust me. Now, I'll let you do number 4 and decide where we are going.
You want me to do the whole thing?
Yeah.
Okay.
Then I'll give you one more and then we'll look at something else.
Okay. It's gonna go to the right.
That's gonna go to the right and you're right.
Okay.
Okay.
I said that
Uh-huh.
I said that was the most acidic. Hydrogen brought the lone pairs over. I did
Okay.
that. And then
Uh-huh.
I got NH3 with 2 lone pairs on the end. Compared
Correct.
acid and the conjugate acid. I compared those.
Who is your acid? This one.
Conjugate, yeah. And then that's the base. And then the conjugate acid, it's that one.
This is a conjugate base.
Oh, sorry.
Yeah.
Yeah.
Then
And
this
that's
is it.
conjugate acid.
Yeah, so you would compare these two
Yeah.
or
And then
those two.
electronegativity.
Uh-huh.
Because of the nitrogen.
Correct. If you're comparing acids, oh wait, tell me why did you go to the right again?
Because of the nitrogen being more electronegative.
If nitrogen is more electronegative, so this should be the stronger acid.
Oh my god. I don't understand why I don't understand this. Okay. So it's gonna go the other way then.
No, actually it goes to the right. Let me think. No, electronegativity will not help you here. It's the pKa.
Okay. So if I just didn't use my brain, I would have gotten it right.
Yeah, that one, if you didn't use my brain. This one is tricky, and the reason is this. Like, just use general knowledge, even without the pKa. This is ammonia.
That's more acidic.
No.
Or less acidic.
Look, it has a lone pair. What does that tell you? He has something to give.
Yeah.
As a base, does this one have a lone pair?
No.
Okay. So here, electronegativity is failing because hybridization is kicking in. But it's a rare case. Anyway, such a question when it comes, think of the presence of a lone pair. If you're comparing, just take this note. Maybe we should add. if you're comparing two acids, the one that at least has a lone pair is going to be less acidic.
Okay, so weaker acids have lone pairs.
Weaker acids weaker acids wow, then that statement will not apply, because if you go HCl, you see that?
That's a really strong acid.
Yeah, yet it has 3 lone pairs.
Okay.
I think, let's say this one technically we should have used pKa to decide.
Okay.
Or if you're lucky enough to remember that ammonia is a base, or it has base, yeah, it's basic in nature, that's where you're going. Okay. Now, that was an extreme, but let's do this one and see. This one is easier. And then you show me something else you want to show me in your test. Try that. By the way, the pKa of ammonia, I think is 36, 35. pKa of terminal alkyne is 25. So it should go to the left, to the right.
Okay.
The pKa here is 25. pKa of water is 14. So we went to the left. All right, so try number 5, then you show me the other concept you need clarity.
Does it go to the right?
Yeah, it's gonna go to the right. The factor we're
Because
using, go ahead.
is it because there's 2 oxygens on the other one? So
That's one, but the main factor is resonance, the R factor of area.
okay. So if there's resonance, it'll shift towards the side with resonance.
Correct.
Okay.
If you're comparing bases, this base has no resonance. This one is resonance stabilized. Anything that increases the area increases with area is gonna be a weaker base.
Okay. So RAO helps you determine which is the acid and the base.
Correct.
And then it also helps you determine which way the equilibrium is going to lie.
Correct.
Okay.
Now, if you go acid, same thing, there's resonance here. Also, you can say there's 2 oxygens. So inductive effect kicks in. When you say there's 2 oxygens, you're looking at inductive effect, electron pull through bond.
Okay.
So 2 factors. Making this one more acidic.
Okay. So that makes this one more acidic and this one more base, or you can't see my arrow,
Correct.
but
More
it makes
basic.
it more acidic.
This one more acidic, this one less basic.
Okay. Okay. So REO helps you determine acidity. So that's how I can think about it with the equilibrium. So if it lacks REO, it's probably a weaker acid. Does that make sense?
No.
Okay.
Again, I'll tell you, depends on what you're looking at. Are you looking at a base or an acid? Here you're looking at a base. If there's more of the area, then you are less basic.
Okay.
If there is more of the area in the acid, then
You're more acidic.
yeah, like here, you're more acidic.
Okay.
That's the idea. And you want to go on the side where you have a weak base, weak acid. So more area on a base, less basic. More ARIO on an acid, more acidic.
Got it. Okay. I got it, I promise.
Okay, good. Now I'll stop sharing and then you share your, let me just minimize my writing pad. You can share the next question you had.
This.
Newman's?
I don't I did okay on these because I had to try and figure it out, but I don't really think my method was correct.
Okay, no problem. We can review.
Okay. There's definitely gonna be Newmans on the exam.
Definitely. Why not? Newman's, stereochemistry, acid base, addition reactions, those are a must.
I get he said on Friday, an outline of what the exam will look like without like the actual questions, if that makes sense. So it'll say like what question's gonna ask without the problem. So I'll send that to you and then maybe we can work through some stuff to make sure I know everything.
Okay. Identify, okay, in each case below, draw the Newman projection. So I usually tell myself if my...
Can I stop sharing?
Yes, am I sharing?
I'll look.
I'm not sharing.
Am I sharing? No, I don't think so.
You're not sharing. You're good. Let me see. Excuse me. Okay, should see my screen.
Yeah.
So when the eye is on the left side, anything on the dash will be on the left. So the dash goes with the side of the eye, basically.
Okay.
When the eye is placed on the right, so these are the rules that will help you greatly. When the eye on right side, so that means that your dash will mean right. Right of circle, left of circle. That tells me that the wedge will be right of the circle, and the circle is always the back carbon. Okay. And here, right eye on the right, this means left of circle. And then plane is just plane. You can be plane up or down, even left up or down, right up or down. So this is on the plane.
Okay, so the dash is always closest to where you're looking down?
No, the dash just means that you are either left or right, depending on where your eye is. Let me show you what I mean. Okay. The eye here is on the left side, right?
Yeah.
So on the circle, where should my dash be on this front carbon? We call that front, this is back. This is the front right here. On the circle, on which side should the hydrogen be?
Hold on. Sorry, left. So, on the left?
Yeah, so it's on the left and up. So LU, this will be RU, and this will be PD.
Okay.
So left and up, this is my left last time I checked.
Yeah.
This is my right and up, and then PD. Plane down. Trust me, it's very simple.
Which CH3 is that? the front one or the back one?
No, we are looking at the front carbon. What's attached on the F?
Okay.
We have not
So then,
started the back yet.
okay.
We have a CH3 on the back,
So that goes at the top, right?
and the hydrogen should be same side as the dash, but a wedge. So this one goes here. Plane, this is PU. It's on the plane, regular
Okay.
line.
Okay.
Where will the blue hydrogen be? On the back. Remember, the circle is the back carbon.
Oh, wait, am I wrong?
That's why the lines are not crossing it. The CH3 is tethered attached to the back carbon, the circle.
So does it go on the left?
No, it's on a wedge. The blue hydrogen goes on the right. Remember, the I is on the left, so wedge goes right of circle. If Cl went to the right, why would not the H go to the right? They're both on.
Why does the chlorine on the wedge go on the left then?
This is where's your right side? This is the right.
No. The did we do that one already?
No, we are not done the blue.
Yeah.
The blue should go to the left because
yeah,
it's on the dash. I had not done it yet.
Oh my God. I think there's something wrong with me today. Hold on. Okay, I'm sorry.
It's okay. You skipped dinner.
Oh, I did.
See what's happening to you.
Studying all day, like frantically. I'm sorry. Okay.
I knew it.
So I'm gonna write these notes down really fast, and then I'll be.
Okay, do that.
So you basically always want the wedge close or the dash. This is why I'm having an issue.
It's nothing like closeness anywhere. Just know if the I is on the left, the dash should be
on the left.
On the left, either up or down, depending on how it's drawn on the chain. There's nothing like closeness to the eye or whatever. No.
Okay.
The only thing you can tell me about closeness is identifying the front carbon.
Okay.
Which is the middle of the circle. That's what I can think of.
Okay.
Closeness.
So for the next one, that's on the right. So on the right side of the circle, we're gonna have a chlorine, right? A CH3 on the straight line because it's on the plane. And then we're gonna have a hydrogen on the left. Is that right?
Okay, say that again. So which one is your front carbon? Because that's the first thing you want to do.
Front carbon is the one attached to the chlorine on the dash.
This one, yes.
Yeah. So I said that one goes on the right of the circle.
Correct, and up.
And then the down one.
Don't run away first. Wait, there's an implied hydrogen.
Yeah, I got that.
Okay, then this.
That is there, yeah. And then I have the hydrogen, yeah. So then for the next one, the hydrogen that's on the wedge or on the dash next to the bromine is on the right. Hydrogen on the right, bromine on the left, and then in the plane up is CH3.
Correct, that's correct.
Okay.
If you just know the rules, all this become easy.
Okay. And then for this one, the front carbon is, hold on, I just want to draw my wedges and dashes. The front carbon is the one with the CH3 on the dash. So then we get the CH3 on the dash on the right side. The one in the plane is that a CH3 CH2?
Yeah, you just add a stick.
Or yeah, CH3 CH2. And then the one on the right or on the left on the wedge is a hydrogen. Right?
Yes, implied.
And then for the other one, I said it's the one like directly attached. The next carbon, like the back carbon, is the one directly attached to the front carbon.
Mm-hmm.
Right? So then, well, I just know the up one is a CH3 CH2 again.
Yes, then you'll have to show your implied
And then,
hydrogens. One has to be dash, one has to be wedged. And they are pointing down because B's wedged down.
and then it's both hydrogens. Yeah.
Yep. And all these are staggered because they are all 60 degrees. If the bonds were aligned, that would be eclipsed, and that's the less stable one.
Wait, what is an eclipse again? When it's like not like that?
Yeah, you also have pneumons that look like this, with the bonds kind of parallel. That's the eclipsed, very crowded, and that's less stable.
Okay. Is that like torsional strain? Does that come into play? Is it that?
Yeah, you have that's the only time you have the torsional, whether you have hydrogens or CH3. That's torsional.
Okay.
It's torsional plus sterics, but sterics will be more than the torsional. And if you rotate maybe the front carbon just by himself, you're going to get the eclipse.
Okay.
Or if you rotate the blue back carbon by itself, you're going to get the eclipses of all these.
Okay, got it.
3-methylpentane.
So I have to draw that.
You have to draw it, so you draw your own molecule and you have to draw your own I. But it guides you. You have to look through C2, C3. So the methyl group is on the third. Okay, it's not chiral, so we can introduce our own dashes.
Okay.
Let's go with a wedge.
Does it matter?
No, because this bond can rotate.
Okay.
You can put the methyl group on a wedge or a dash.
I hate these.
You don't have a choice, my dear. No choice here. It is what it is. It is what it is. C'est la vie. It's life. Such is life. So we need to look through C2, C3. If they said C3, C2, then our I would be on the right. So once you establish that, we'll get our first staggered. We'll call it S1 and then rotate to get S2, and then rotate to get S3. You always have 3 staggered, 3 eclipses.
Okay. So the one in the plane of the front carbon is a CH3, and then we get an H and an H. And then we get CH2 or CH3, CH2 for that one, and then we get Is this right?
I can't see unless let me come back to Google. Show me.
Can you see it?
Yes, I see it. Just a moment. Hold it.
Sorry.
1, 2, 3. 1, 2, 3. That's correct.
Okay.
See, you are master of this now. I'm jealous. Am I? No, I'm not.
So, what does it mean by draw the most stable one?
We're coming. You're coming. Don't go ahead of yourself.
Okay.
Learn slowly.
I remember.
Huh?
This was an exam question, I remember.
Okay, so remember this is a staggered one. So you did put CH2, CH3. No, I'm not gonna do the CH2. I'm just gonna put a stick. I'm going to put a stick on there.
Okay.
For clarity. So, the back one was red for me. Yeah, CH3 goes to the right because the I is on the left. Side is left. And then hydrogen goes here. And then coming to the blue, yeah, you're right. Hydrogen goes there anyways. And then CH3 goes here. Now, if you want to get the next staggered, move things 120 degrees.
Okay.
If you go 60, you get the eclipsed. So rotate 120 degrees. This is gonna come here, and let's just rotate the front carbon.
Okay, so then the CH3 would be up on the left, and then we would have hydrogen up on
CH3,
the right.
yes. Well,
And
there nobody will know which hydrogen was which, but anyway, that's the idea. And then we
leave the back carbon.
leave the back carbon alone the way it is.
So only do one at a time, never do them. Well, you can't do them both because you'll keep getting the same thing.
You're going to get the same thing in a few steps here. So you do it again, 120-degree rotation.
The front carbon again.
Yeah, just do the front carbon. So that tells me my CH3 is gonna come here, my baby hydrogen there, and then keep things the way they are, and then I'll answer your question. What does it mean to be more stable? Okay. I'll wait on you.
I'm good.
Okay, so now you want the least crowded staggered, the least gouge. 60 degree, when two groups are 60-degree close, we call that gouge. So let's see which one has the least gouges. Okay. I'll just get this cloud here. Let me change from here. So this is a gouge. You don't want it. We call it gouge interactions.
Is it because it's a CH3 and a CH3?
Correct. Okay. Hydrogen does not crowd with anything. So this one has only one GI.
Okay.
And then we go here. Oh, there's a nasty gouge there. Ethyl and methyl, and there's another gouge here. Okay. This S2 has two, let's call it gouges. And then this one is a gouge here. So this guy, you see, you don't crowd with hydrogen. This has two gouges. This has one gouge interaction. Okay. However, you have to decide between the two of them that has single gouges, which one is better? You have CH3 to CH3 gouge. So one gouge, CH3 to CH3. Here you are. Huh?
I think it's CH3 to CH3, right?
Yeah.
Yeah, because the other one's bigger.
Thank you. Okay. So S1 is more stable. That's the idea.
Okay.
Mm-mm. Now for Eclipse, they will ask you for the least stable.
Okay.
You want the one that has so many big groups together. If you have a CH3 parallel, if you have a CH3 parallel versus one that has a CH3 and ethyl parallel, that will be the least stable.
Okay. I'm gonna look at an exam because I think I got this question wrong. One second.
Uh-oh, where was I?
Not here.
Okay. Because I doubt I was there.
Yeah, it's my own fault.
No, it's okay. We hope that you get your A anyways.
Oh wait, no, I don't have it. I got the question, but it was one of them was the least, and then one of them had equal stability.
Yeah, you definitely find the equal stability would be the one with will have the same groups
Okay.
crowded. Yeah.
Okay. So if, for example, in the one that we just did, if there was another CH3, there would be equal stability instead of the CH3.
CH3.
And
If
there were
if
like two of those.
if you rotate them and you have CH3 close, then that would be equal stability.
Okay.
However, never compare an eclipse to the staggered. Always the staggered wins.
Okay, got it. Okay. And then with axial and equatorial positions, it's axial, is that the wedge, and then equatorial is the dash?
No,
That's
you're
how I.
mixing yourself up.
Okay.
You are talking about something different.
Yeah, like with chair confirmation. I
Yeah.
have another example if you need.
Oh, okay. Just share so I can quickly show
Let
you.
me see. Methylcyclohexanate.
When you have
Okay.
a dash, it can be axial down or equatorial down. When you have a wedge, it can be axial up or equatorial up.
Oh,
So it's
okay.
not automatic. You really just have to look at your molecule and decide.
Got it. Sorry.
Let's see. Oh,
Sorry, this one. Like one of these two will work.
okay. Oops. Let's see. I need to screenshot that. You can unshare now.
Okay.
Let's see what you got.
Wait, so what's the rule with axial? Axial's up, equatorial's down?
No. You can have
Really?
axial up, equatorial up.
Oh yeah. So it's
Axial just means straight up, straight down. So I'll show you. Just a moment.
so is it wedge up?
So you see this?
No, I don't think you're sharing.
Oh, you're not. Okay, I should be sharing now.
Yeah.
So this right here is axial down.
Okay.
This right here, just keep going out of the skeleton of the ring. This one is going up, so this is straight up, axial up. See how
Okay.
this bond is going up?
That's equatorial.
This is equatorial up.
Okay.
Now, if I draw a hydrogen here, that's gonna be equatorial down.
Okay.
Anyway, let's go back here. Draw.
Wait, so sorry. What deciphers axial versus equatorial? I know it's with like one's a wedge and one's a dash.
No.
Really?
If I have a, let's just answer this question.
Okay. I'll be patient.
Methylcyclohexane, right?
Mm-hmm.
But that one will not help me. We'll use one that has a weight, but that is not helping. Let me quickly show you something.
Okay.
You see this molecule?
Yeah.
I usually just mark one of the carbons. Let me mark this and assume it's that. If you're doing the flip, it's not the pancake flip. You're just pressing these carbons up and down. So always this means up. It can be axial or equatorial. The dash means down, which is what I keep correcting you. It can be down, axial, or equatorial. Okay? So,
there's one up or down.
yeah, it just now depends on your chair. If my carbon is pointing up like that, if my carbon is pointed up like this, I will always have one axial. So that bromine has no choice but to go straight up. If this, okay, let me go, skip 2 carbons, 1, 2, so I'm here. That is down, and my carbon is going down. That means my axial has to go down. Okay? So my axial has to go down, but what's on the axial? The tach butyl.
So then if you flip it, that's when it can become equatorial.
It becomes equatorial, but it keeps its upness, and this one's gonna keep its downness. That's the idea.
So they don't switch where they're going, they just switch if they're axial or equatorial, which is just how you draw the line.
Yeah, it depends on your chair, how it looks. That's what determines if you're going equatorial or axial. So after the flip, axial down interchangeably is gonna go equatorial down. You keep the downs, you keep the ups. Axial up is gonna go equatorial up, and equatorial up can come back to axial up.
I was getting very mixed up.
Yeah, so for this one, if I mark this as my carbon, the metal group has to go, because the axial will be down, and it has to be my hydrogen, which means my metal group will go here. If I flip it, this carbon then should point up, and because this is equatorial up, I have to be going axial up. Which one is more stable? This one. The rule comes in. Rules. Most stable chair has most in terms of number and size. Most B groups on equatorial. Why? Because you want to prevent 1,3 diaxial interaction. So like here, there's a hydrogen. That's what you call the 1,3 diaxial.
So
interactions.
You would want pH3 in equatorial over a hydrogen.
Correct.
For the stability.
So if I flip this, is the same thing. I'm almost going. The Cl will go here. The hydrogen is up, is gonna go axial up. Metal group equatorial up. And this one is gonna be the most stable one.